Hello and welcome back to Calculus 1 Saturday edition. We are talking about section 3.6, derivatives of rate of change. And we are going to talk about the instantaneous and also mention average rate of change, which is the old stuff from algebra. That's going to be your m tangent slope, right? M tangent versus m secant. Those two slopes we talked about in 3.1. So what is this section talking about? Well, if I mentioned before when I talked about the concept of the derivative that you have the m secant to be f of b minus f of a divided by b minus a, and that was the basic slope of the line from algebra, and we call that the average rate of change. And the use for this would be, for instance, when you're driving, you go 0 to 10 miles in distance in 10 minutes. So you would say that's 10 miles, right? The rate, which turns out to be velocity. Rate would be 10 miles over 10 minutes, which is 1 mile per minute. Now, you don't like miles per minute, you like miles per hour. So you convert your minutes to hours. So you want to cancel minutes, you put them up there. You want to have hours. So now minutes and minutes cancel. 1 hour has 60 minutes. So you have 60 times 1, 60 miles per hour. So this means that if you drive all the time for the entire 10 minutes, if you drive exactly 60, you will cover 60 miles of road to you will cover 60 miles. So that's approximately our college to New York, approximately 60 miles. And you should be, if you're always going 60. So that means that you technically live on a highway and you get in a car and then you just push the gas pedal till you get 60. You put the cruise control, you will be in New York in 10 minutes, driving 60 miles per hour. Oh, sorry. No, New York is not 10 miles away. What am I talking about? New York is about 60 miles away. You will be 10 miles of distance, 10 miles of distance in 10 minutes. Because when you are doing 60 miles per hour, there we go. When you're doing 60 miles per hour, you are covering 1 mile per minute. That's what it is. And that's the average speed. Now, are you driving 60 miles per hour when you start? No, your car is parked. You have to get in, right? So this is not the actual, this is the average. You go above 60 miles, you go below 60 miles as you are driving. Maybe you have to stop at a stop sign, a red light, right? So all of those things are there. Now, how about if you look at your speedometer? We said that that's called instantaneous rate of change. So instantaneous rate of change, I'll write that one in red because that's the one that we are actually interested in. Is your derivative. So instantaneous rate of change will be given by f prime of x is equal to the limit h goes to 0 of f of x plus h minus f of x divided by h. But hold on, didn't we just learn a lot of those shortcuts to compute this? Exactly. So we don't have to compute this formula anymore because we know how to obtain that answer by using the shortcuts, because we memorized shortcuts. Now, you might say, well, why do we need this formula? We need this formula to understand that, look at this, age goes to 0. The time frame at which you are looking at goes to 0, so it's infinitely small. That's what it is. See, it takes time to brake and reduce your speed, which is why you have a speed limit of 25 in a residential area, because a kid might run out of, a 5-year-old could run out on the street after the ball, right? And if the speed limit is not 25, you're driving 70, you can't stop that quickly, right? So it's important to understand where these speed limits come from. And some of them, obviously, are there because the stopping power of the car, right, is not that great. So the brakes, right? And even if you have great brakes, what kind of tires do you have? Are they brand new and have a very good grip? Or they're going to slide a little bit, right? What is the engineering for the brakes? ABS, how well that works, right? Anti-locking system for brakes. All of that stuff is very important. And see that instantaneous change, you are looking at the infinitely small window of time. So the laser that it's clocking your speed when the officers have the speed traps on the highway and so on, the window for that laser clock is fractions, tiny fractions of a second, right? You don't have time to brake, right? Even if you have seen the car, you're clocked long time ago, right? Because this age goes to 0, the window at which you are measuring that speed is going to be very, very, very small. So when you look at the speedometer, that's how fast you're driving in that instant. Press gas, it's gonna go up, but it's not going to go up instantly from 35 to 50. It has to go through every other speed in between gradually. Now, the cars that are designed to do that quickly, we call sports car, right? And you have the other cars that are not sports cars, that they're achieving those speeds slowly. So you are going to have the difference between acceleration of, let's say, Prius and Tesla Model S with ludicrous button on it, right? It's going to be huge difference. They're both cars. They can both accelerate. They can, right? But it takes a different time. Now, the trick is that we are not talking about how long it takes. We are going to understand that even for Tesla Model S, it is still going to take time to accelerate between 35 and 50, because you have to hit every speed in between, and that takes time. It takes shorter than if you're doing the same thing with Prius, but still, Prius will eventually get there, right? It will take longer, but the Prius and Tesla would both be going at 50, right? So that's something that yeah, my friend just in a separate chat said Prius can go 50 with a question mark. Anyway,
I was gonna comment something like that, but I figured better not.
Why not? I mean, I'm all for fun and games. I mean, it's fun, and I have a dear friend who drives Prius, so that just adds to the fire for the later arguments. So yeah, why not? Go ahead, troll. I don't care. Anyway, so the question is not how fast you raise or lower the speed. The question, because that's acceleration. or deceleration if it's brake, still negative acceleration. The question is, when you look at that speed, it can change either way in an instant if you touch gas or brake pedals. So your instantaneous speed measures the speed of the moment, where the average speed measures the speed over time. Okay, so now that we clear that up, we're going to say that there is the position function. And usually denoted as S of t. It's a function of time because your position depends on the time, right? You know what the Joker says, depending on the time, it can be in one place or several. So the thing is, if you are driving the car, position is going to be where are you on the road from point A to point B. You can be at the position 0, that means you just got into the car and you are getting ready to leave. Could be at the position B, which means you arrived at your destination. But you can also, you can have the any position in between. And all of those positions depend on the time traveled, which is why its position is a function of time. Where are you now? Where are you going to be in 10 seconds, 30 seconds, 2 hours, 5 hours, and so on. Let's say you have a long trip. You go to, I don't know, South Carolina. How long will it take to drive? And you're not making stops, right? 5 hours from now. How far into are going to be? So position function. Now, when you take the derivative of position function, you get the velocity function, which is also a function of time. So change in position in time is going to be velocity, v of t, which is velocity function. And we had that earlier when I told you that the position function was given by that e to the negative x cosine, and then you and then that e to the negative term is the one that actually kills the motion over time. It's called dampening, and you'll learn about that in differential equations, right? So you can see the change. This d is a lowercase from the capital delta from Greek, right, which we use for change. So change in position in change in time, because it took you some time to get from point A to point B. When you are in a point, point B, you had the time that passed to get to get there. So you have that, and then you can change velocity. How you change velocity? Well, you also change it in time. It takes time to press the gas pedal or to press brakes. Both of those are acceleration. Both pedals are acceleration. Brake is acceleration because it changes velocity. It changes it down, but it changes velocity, changes how fast you're going. So change in velocity is called acceleration, and it's also a function of time. And now you can compute the acceleration. We have acceleration due to gravity of 9.81 meters per second squared. Or if you want to use imperial units, it's going to be 32.2 feet per second squared. So that is acceleration of gravitational field on Earth. And obviously doesn't apply elsewhere because on the moon you have a different gravitational pull. Mars has a different gravitational pull because it's smaller than Earth, right? And when you take some of these other planets, take Jupiter that can fit more than 1,000 Earths inside, so it's more than 1,000 times bigger than Earth. Then their gravity, right, is way bigger, right, than Earth's gravity. If you could stand on it, right, you would be crushed. So these are the things that you have to understand in terms of there is a position function that is some kind of a function that measures the distance from where you started, and then you can calculate the velocity function and you can calculate the acceleration functions. There is also another one. The change in acceleration is called jerk. So you can also do that. dA dt is equal to j of t. You know that if you change your acceleration very quickly, I mean, this one is not covered in calculus, so I don't have to put it on, but I just want to connect this as much as possible to your what I would call, again, a real life experience, because calculus is fake. Take a look at your car. What happens when you slam on either of the pedals? Your whole car, your body jerks inside the car, right? So you either are getting buried back into the car seat, which is why you have that headrest so you don't break your neck, or right, you are smashing your face into the steering wheel, right? If you push brakes really fast. So usually you don't get to accelerate that fast, right, to get buried, but you could be hit from behind, and then you would get so much more acceleration that, right, your head would jerk back, right? That's so when the acceleration changes in time, so you can press your gas pedal slowly, in which case your body doesn't jerk, or if you press it really hard, you would get that little, right, bounce in the back into the seat. But you feel it much better when you have to brake very harshly, right? So if a deer, not if, when, because you live in New Jersey, it's not if, it's a when the deer jumps out in front of your car, right, you might slam the brakes, and then you experience that jerk in the direction of the steering wheel, right? Which is why we have airbags, right? In these cases. So all of these concepts make sense, and in order for me, so if we take this jerk function off the discussion now and just focus on these, when your car is parked on the street or a parking lot or whatever, and you are about to go and drive, you're not getting anywhere because your velocity is 0. You have to first push the gas pedal, which is acceleration. That acceleration changes velocity. That takes time, and then you have some velocity. And because you have velocity, right, because you have velocity, the position starts changing, which also happens in time over here, which in fact changes the distance of how far you traveled. So now it all happens at once. Now someone was going to say, is this a chicken or an egg story? There is no chicken and an egg story. Every time someone asks you the question or figuratively says, oh yeah, what came first, chicken or egg? They came at the same time. It's called evolution, okay? But this is happening exactly the same way, right? It's not that acceleration started first, right? No, acceleration instantaneously caused all of the other things to happen, right? So the chicken and the egg, they happen at the same time, like everything else in evolution happened at the same time. So you cannot say, the distance. I mean, you can say the distance was covered because I was driving at 60 miles per hour, and I'm driving 60 miles per hour because I pushed the gas pedal. That is actually correct thing to say, but mathematically and physically, as soon as you touched your acceleration pedal, all of these concepts kicked in instantaneously, because you started changing the velocity from 0 to whatever number, and at the same instant, because there is velocity, you cover the distance. So there is no acceleration first and then, right, acceleration first and then this and then this and then this. They happen at the same time, but it cannot start with, it cannot start with covering the distance. It has to start with you pushing the gas pedal. So the same thing happens with, now if you actually want to introduce jerk into this story, right, then it actually starts there, right, because your foot is the one that hits the brake pedal, sorry, the gas pedal. So how hard did you slam it, right? And then, you know, jump through all of these hoops to get to the distance covered, right? And you can definitely, I mean, if you've ever seen a drag race in your life, you will know exactly what I'm talking about, especially for some cars that have the front side of the car go up in the air as they launch. So all of these things, right, happen. I'm going to take off the jerk off because it's not part of calculus. You have it in a lecture. You can go back. You can see the whole story again. I just don't want to keep it in because you might try to find a reference to it in a book and it's not going to be there. Then you have to look for physics literature and fit it in. So I'm just going to keep it off. So you have all of these here. And what did we say that these measurements are? So we'll say that this is in meters, and then this was in meters per second. We can do feet as well. And this was meters per second squared, right? Now, you can see that your speed, you can also say miles per hour. You see that you have the distance and then you have the time, distance divided by time. But that happens instantaneously because we are dealing with the derivative here. So miles per hour or meters per second. Now, if you take a look at the one on the bottom, we can finally talk a little bit about that Leibniz notation for the second derivative, which now makes a whole bunch more sense. Remember that we said that the second derivative can be written as d squared dt squared of the function, and now I'm going to put s of t inside. So I hope that you see that it is the derivative in time of the derivative in time when you look at written in this form. And if this one over here brings me meters per second, here is another over second to give you second squared in denominator. So the first derivative will give you meters per second, and this one will introduce another second, and that gives you meters per second squared. So that's a little bit of notation, a little bit of dimensional analysis to connect all of these things to physics. Obviously, it's also explained in the book, but the idea is that your position S is only given in meters or feet or miles, whatever, it's just length. And then when you differentiate in respect to time, which you take the derivative in respect to time, you get the formula for speed, for velocity. And then if you differentiate one more time, which is the second derivative of the position or the first derivative of the velocity, you are going to get acceleration, and that one is meters per second squared or feet per second squared. And that's where the gravitational acceleration due to gravity, right, which we call g, is that good old 9.81 or 32.2 feet per second squared, if you will. So now, what can we do with this, right? Well, you have some kind of an object that is traveling with some position function, and you can take the derivative to find its acceleration, the velocity first and then acceleration. Now, I did explain earlier, and I'm going to use the same example again, of that pendulum that is hanging on the ceiling. Now, you do have more of these explanations in the book with other examples, so please look all of that stuff up. So these are the positions of the object, and it takes time for this object to go left and right. Now, there are two ways in which you can set this system in motion. One way is to pick up this bob, right, this ball or whatever, and then pull it to this location and let go. In that case, you have some e to the negative x t, sorry, e to the negative t cosine t as your s of t. Or you can flick it, smack it, right? When it's in this position, can anyone tell me what would the model look like if you just smack it from that equilibrium? So it goes this way first. So you just go and give it a smack this way, a flick or a smack. How would that change this formula for position? Position formula. What do you think? I'll draw the picture for this one again.
Well, velocity is starting at rest if you hold it out and let go. If you flick it, then velocity has a value.
Initial velocity, yes.
Initial velocity does,
but that's
yes.
a velocity. You are talking about velocity. I'm asking about the position function. We are going to get to your place. Exactly. And that's going to be the key point of what you just said. I'm asking about the position though now. How does this formula that I boxed in, how does this change if instead of pulling the object out and letting it go, if I just smack it to go? This is where your engineering is born, by the way. And I'm not joking.
Is the whole thing negative?
No, if you put a negative in front of this, so your suggestion is to put this negative sign here. What I'm going to say is that will be this. If you put a negative.
I was interpreting that as if that is the final displacement. That's my fault, though.
No, that's not a fault. I'm just saying that your equation is still valid. It's just that you are not stretching it this way and letting go. You are stretching it this way and letting go. And that should be actually the little key on what actually would go here. Just by what you just said should actually be enough for you guys to figure out what kind of equation would go here. Look at also the picture. This is where equilibrium is. This is where that negative thingy is. This is where the positive thingy is for the equation number 1. What goes in a box?
So 0?
Nope.
Cosine of t?
You are very close. E to the negative t sine t.
Killing me.
Yep. No, look, practicing, and now you will understand why. Look at the graph of it. So, your displacement was at 0 because the object was at rest. So we're only looking now at the case 2. Object was at rest, right?
Yep.
So there is no displacement to the left or to the right. This is the one that measures distance. And this is the time. So no displacement. Now someone did say 0. Yes, at that instant was 0. But over time, the object will go, you smack it this way, let's say. It's going to go the furthest possible this way. And then it's going to go this way, but it's going to lose some energy because of the gravity and air resistance. So it's going the other way, and it has less displacement from 0. Then it's going to go back this way. It's going to lose some energy, so it's going to be less and less and less. You can graph this exponential function this way and this way. That shows you the tube which squeezes the sine, or over here squeezes the cosine. There is exponential function which is e to the negative t, and we know that that function graphs this way, right? From exponential. So you can see how this rate of change plays the role. You can see how this rate of change plays the role because it will be losing energy as it goes, and also your initial how you set the whole object in motion is important. Are you going to pull it out and let go, in which case it's a cosine because you went as far distance as possible, and then every next time there will be less distance when it swings either way, until eventually sometimes in time it stops, right? And it stops, why? Because e to the t goes to 0, right, in the limit. So this is called harmonic motion with dampening, right, which means it actually stops. You can kick this term out, and in that case it will go forever like this, and that's why we see stars, for instance. The interesting thing, and a lot of people actually, which is, I don't know, to me it's surprising, but I guess it shouldn't be the way the education is. When you see a star, you see a star as it was millions years ago. You don't see a current situation because these stars are so far away that even light will travel for millions of years and hundreds of thousands of years because it's so much density. But because there is nothing to slow this down, there is nothing, so it just keeps going in the same rate, and then you get to see the star, even though that star might not be there anymore. Maybe when supernova 40 million years ago, and we don't know that because we will know in 40 million years when that light from that supernova reaches us, because it always takes time, right, for light to travel. Now, we don't perceive that here on Earth, right, because when you turn the light, it's instantly on, but it's a pathetic distance when you compare it, you to the light bulb, and then you compare yourself or the planet to a distant star that it's, I don't know, 100 light years away. And a light year is a distance that light, which is the fastest thing out there, travel in 1 year. That's what a light year is. It's a distance that light travels in 1 year. That's insane distance. It's insane distance. So when you take a look at the stars, you always see the very, 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 very distant past. So if you are looking for alien life and you receive an alien signal, that signal could be 40 million years old, could be, right? Which is why you are not receiving alien signals, right? It definitely has to be life on other planets. There is no doubt, with the sheer amount of planets and solar systems and in solar systems in galaxies and same amount of galaxies, it's retarded to think that we are it for the universe. That's the mildest I can put it. Clinically insane to think that we are the only life in present. The trick is that if there is a sufficiently developed alien race that can send signals out that surpass us in any way, anything we are receiving is going to be so old because it can most travel at the speed of light, right? Electromagnetic waves, Maxwell's equations. So you can look that stuff up, but it's gonna, be there when you do Calc 3 and you do Physics 2 in a course. So you can understand these kind of things. But everything happens in time, and the distance will be measured in time. So when you do that change in distance over change in time, you get that speed at which something travels. So now, if my position function, as I said earlier, s of t, is given as any one of these. Let's do the sign. Let's say you smacked this one. So e to the negative t, that will eventually slow it down and make it stop. And then sine t, because we smacked it rather than pulled it out and let go, right? Because you can, right, pull out this way and let go, it will start swinging. Or when it's at the equilibrium position, you can smack it and it will go left and right. So now, let's say we're going to do the smack. You have the position. Now, to find your velocity, all you need to do is to differentiate this. And this is where your product and derivatives, right, product formula and the derivatives of E and sine kick in to come up, right, which is what we did the last class. So now you're going to say copy the first, derivative of the second, plus copy the second, and then derivative of the first. And we factor out e to the negative t, and then we get cosine t minus sine t. So now you want to find acceleration for this object, which will be the derivative of velocity, right? Because acceleration is change of velocity. That means you differentiate velocity. So now we have the derivative of, and now I have this, which is another product rule, a little bit more involved, but we can still do it. Over here we have cosine t minus sine t. So what I would do here is, again, I have my u, I have my v, and then I unleash the product rule formula. Copy the first, derivative of the second. Derivative of a cosine is negative sine. We learned that last lecture. And derivative of sine is positive cosine, so the sign will not change. This sign doesn't change because derivative of sine is cosine. And then I have plus. So all of this was copy the first, derivative of the second. Now I need copy the second, cosine t minus sine t, times derivative of the first, which is minus e to the minus t. Now we simplify this by kicking out e to the negative t, and we get, what do I have in parentheses? If I put this out, then these guys stay as they are. Actually, I can kick out negative e to the t and then change these signs as well. Or I can do this sign over there. It doesn't really matter. Yeah, let's pull out the negative, it's better. One step less with writing. So now these guys will become sine t plus cosine t. So those are these, right? And then, since you took the negative out, you are taking this negative out. So all of the signs will stay the same. So I get plus cosine t minus sine t. It's a little bit of algebra. This is where sine dies. And cosines, cosines pile up. So derivative of cosine is negative sine, derivative of sine is cosine, then copy cosine, negative sine, and then copy this one. Okay, so I should have this, and then a 2 in front, and then cosine t. Here we go. So now I can ask, what is the position after 2 seconds? What is the velocity at 2 seconds, the speed? And what is the acceleration at 2 seconds? And I simply get those numbers by plugging in t equals 2 in each one of these equations. So if I want to say, if I say v of 2, that means we calculate velocity at t t equals 2, let's say, seconds. So literally you're just plugging in number 2 right there and number 2 right there, and that's going to give you some decimal over here, and you have your answer, right? Plugging in. Now, if you want to say, well, can we not have 2? Can I do pi over 4? Because that's easy to compute here. Well, you're going to pay it right there because you're going to have negative pi over 4 in exponent of exponential function. So you can't win. Okay, you can't win. It's simple harmonic motion. Can you imagine what the complicated harmonic motion looks like if the simple one looks like this? Yeah. Bring it up next time when someone tells you you're stupid. Bring this up, see how well that goes. But first understand it very well, all right? Because you don't want to get these things wrong and confused, and then, right? So learn it well and then use it, right? Then use it to shush others. So there we go. We have this as an example, and we can calculate S of 2, which is position at 2 seconds. We can calculate acceleration. We can find another derivative, calculate jerk, right? So you can compute these things now. This is the part where you now learn calculus. I gave you one example of the harmonic motion where we had to use product rule to find all of these derivatives, right? What if this is not a harmonic motion that stops? What if it's just a harmonic motion that goes forever like this? Then you just have a sine function there. The calculations change. What if it's a parabolic motion, the one that it's explained in a book, and I'm not going to go through it because you can read, hopefully, right? You all know the letters and all of the letters and numbers, so you can read those examples. But for parabolic motion, you throw something from S0 5 feet height or 6 feet height, whatever, and it goes in a parabolic motion and it falls to the ground. There is an equation for position function S, which is the function of t, which is the height of the object going through, and it's negative 1/2 gt squared plus v0t plus s0. We derive this formula in Calc 2 from gravity. We derive this in Calc 2, and then again in differential equations. We derive it from scratch. Right now, you might know, you might not know this formula from physics. Most likely, you don't know it because in physics now you get the formula sheet, so I don't even know why you have the class for the exam. Because the only thing you should learn in physics are concepts and formulas. If the formulas are given on the test on a piece of paper that you can bring in, I literally don't understand what you're learning in there. But okay, fine. Going to this thing now, I can take velocity derivative, right, which is ds dt, and come up with negative gt plus velocity 0. And I can take for acceleration, you'll just have negative g, which is exactly what you are expecting because we said acceleration due to gravity. Well, yeah, right? That's your 9.81 or 32.2, depending on which system of units you want to use, imperial or metric. So if I want to know where is the object after 4 seconds, position for the object 4 seconds, velocity of the object at 4 seconds, and due to gravity, acceleration is always g. So these are the things, right? This is the vertical motion of the parabolic motion. For the x motion, the horizontal one, you are using that good old distance equals velocity over time. There is no so this is vertical and this is horizontal. So you understand all of physics and kinematics very, very easily. And if you involve, a little bit of trig in here, you can go with rotational kinematics, right? For those angular velocities and angular acceleration, which are having the same formulas because it's the same kinematic, except your path is not a straight line, it's a curved theta angle. So you get your those values that you see if you were just mindlessly memorizing or copying formulas. It did not click, but you have acceleration alpha, which is angular acceleration, and then you have angular velocity omega, which was velocity, that was angular, and then you have the position s or y or x, in this case theta. All of the formulas look the same. It's just with these variables. So you can literally take Control C, Control V, and just swap these swap the letters in for angular velocity. It's all the same. And then there is the connection between the two worlds. Physics is insanely simple and cheap if you understand basic principles of calculus, which is the building block. There was no physics, there was no engineering, and there were no cool toys prior to Newton's development of calculus, and Leibniz, obviously. But Leibniz did more for economy and stuff. So that's your kinematics. That's the way you use derivatives, right? You take the position function, you differentiate, get the velocity, you differentiate, you get acceleration. Derivative again, you get jerk. And now, hopefully you will go to the book and take a look at one or two examples they gave you for this one, for parabolic motion, right? Which is again the distance in time. Another concept where you can use derivative as a rate of change if you want to measure the change is, let's say, population for biology. If you take a look at the rate of change, you can calculate the rate of change of population if you have the population. So in your pre-calculus course, you memorize that population model was given by population in time is equal to initial population e to the kt, where if you want to have growth, your k is positive, and if you are having decline of the population leading to extinction, it's going to be k is going to be negative. And even though this is the worst possible model, you will fix that when you take differential equations, because you will learn, there will be a whole lecture on how to fix this bad model. Now, why is it bad model? Because when you start with your initial population, it tells you that in time, your population will grow to infinity. You cannot have infinite population of anything on a planet that it's a finite size. So this population model on the long run is bad, but it works well locally. So if you have some population model, which is, let's say you start with 500 units of something, whether it's amoeba or humans or rabbits, I don't care. You have 500 units, and then e to the 0.003t. So let's say this is population model given. They observed the points at different times. They know they put in initially 500 rabbits on this island that did not have rabbits, and they came up with this model. You can use the model to compute population at time t. So, how much rabbits do we have 3 years later? You stick in 3. How many do we have in 10 years? You stick in 10 for t, right? And once you plug the 10 in, you will compute the amount of rabbits present on the island. Now, that's all pre-calculus. You being able to compute this formula with t given as a certain value, that's your pre-calc. What I want to know here, I'll write it in blood, is change in population. And that, my friends, is the derivative of the formula in time, right? And now I need to be able to take the derivative of this. So your calculus exam is going to ask you to compute population at some time. But that's part A, and that's 3 points. But then part B is asking you to compute this, and that's 7 points. Because you have to find the derivative, which is you copy the constant, and then we said when you have e to the at, it goes to a e to the at. So you have to drop that a, and then copy the function as is. Oops. 2 zeros, t. So now you multiply these two numbers. So 2 zeros will knock off 2 decimals, and then 5 times 3 is 15. So this is the same as p prime of t is equal to 5 times 0.3, because 2 zeros would knock off this, e to the 0.003t, and you would have your population, the change in population, to be 1.5 e to the 0.003t. This one is only measuring the change within the unit of time you have. So if your unit of time is 1 year, it will tell you how many more rabbits you have in that 1 year than the previous year. So you will, this formula kind of calculates the difference, how many additional rabbits you have in that 1 year, because it's calculating the change in population. Remember, that's what calculus wants. Calculus measures the change. It's not measuring current population. Current population is pre-calculus stuff. You can go also and count it. Calculus is going to tell you that when we say we added extra 115 rabbits, that's a change in population from 500 to 615. This 115 rabbits came from here. The change in population which you measured with derivative, right? So that's what we are figuring out in case of change in population. And now from here, change in anything is measured by taking the derivative. Instantaneous change. Remember earlier I said change of position is velocity. You measured the change of position while we took the derivative. You change velocity, that's acceleration, pressing the gas pedal. We did change in velocity, and that gave us the derivative, gave us acceleration. Now, change in population, it's derivative again. Any time you hear the word change in something, it's the derivative. So that's the key. That's your entire differential equations course, right? And you will see in that course, as well as in Calc 2, how you come up with this formula over here, starting at the sentence, the change in population is proportional to population, which makes sense. More people you have, population grows faster. Less people you have, population grows slower, because simply more people, more pairs, more babies. Less people, less pairs, less babies, right? There is a limit of how many baby, right? Babies people can have in a period of time, right? You can't have a litter of 25. That's not possible. So this is a thing. I mean, in a year, maybe there is a case with 25. I don't know, but I'm saying it's just that you can't have 25 babies in a year. I can sign that statement pretty much. So the change in population is proportional to population, and then you do differential equation, you come up with the formula here. Now that's obviously for later courses, but that wording, change in population, your differential equation starts with dp dt equals to kp. That's the differential equation. But again, you don't need to know any of that. It started with change in population is. And you need to know that right now. Anytime you hear the words change, we'll have two sections that will exclusively have derivatives and so on as word problems. So we'll learn it there, but the more you learn now, less you have to learn later. The last problem or formula I want to talk about is business and economics. And we want to take a look, and I'm actually, this is one of the rare cases when I work out the problem that is given in a book, because it's such a great problem. We're talking about the average and marginal cost, and it's an amazing example which shows you the difference between average and instantaneous. Now, in business, I guess the word derivative and the word instantaneous are way too difficult or scary or whatever. So they came up with the word marginal. So if you are a business major, the word marginal means the derivative. So if you, once you take a look at this average and marginal cost, the average is the good old slope formula, and the marginal is the good old derivative formula. So average cost, let's go purple. Average cost is going to be the cost function divided by total of units produced. So average cost is cost function divided by units produced or made or whatever. So in our mathematical terms, C of x divided by x. Now, cost of units. In order to make anything, you have to have cost. You have to have materials from which you make things. You have to have the workers maybe, right, or a machine. You have to have machines and tools, and that costs money. All of that goes into a building that costs money. When you make whatever you're making, you have to transport that to the stores where people are going to buy it, or to the warehouse where people can order it online and buy it. So transportation is also the part of the cost. So the workers' salaries, machines and their maintenance, and so on. Why is Tesla S so expensive? It's ridiculously cheap to make in comparison to the car with the engine. It doesn't have thousands of moving parts that have to perfectly fit. It only has electrical motor and a battery and a couple of wires and a software in a computer. It's a joke to make Tesla in comparison to any of the gas-powered cars. Why is it so insanely expensive? Well, the machines, which costs millions upon millions of dollars, and buildings, those things did not exist. So Tesla had to develop and invest insane amount of money, and they need to pay that back. They need to make that before they can start making profits on these things, right? And when you have a well-developed factory, like let's say Nissan, that produces cars for decades, they come up with a new body, right, model for a car. They just turn a few knobs and here and there modify the machine. They don't make a new machine from scratch, right? So there is a huge cost to make something that never existed before, and less cost, obviously, to make a new model for something that already exists, which is, I think, a ripoff to pay every year $1,000 for a new model of the phone. I mean, if you're doing that, you're an idiot, but getting a phone every year. But because these things last like 4, 5, 10 years can last, if you don't abuse it, obviously. But the thing is that if you take a look at the cost, having the phone always cost $1,000 when you are marginally changing your profit, only the new products should be insanely expensive because obviously the cost of making those. Right? That makes sense. And then you have the marginal cost. And that's just going to be the derivative of your cost function. And now to understand that, there is this amazing problem in a book which helps you understand how you can make good business decisions. And this is where, let's say, Elon Musk is absolute God, right? And why he is able to run 10 businesses and be successful in all of them, right? Understanding the cost, understanding the market, understanding what people really want, right? And thrive without ripping people off and like for instance what Apple is doing, which is disgrace. You can take a look at Musk, right? So cost function is something that mathematicians or people that do economics and so on, who are very good with mathematics, they're going to come up with this function which has variable cost and the fixed cost. I don't want to go into the details of, most of you are not business majors, so maybe it's worthwhile saying. Variable cost is the cost due to amount of units and materials that you are using to make a product. So if you want to make anything like I don't know, plastic markers for whiteboard, you need plastic, and it's going to be different amount of plastic you need if you want to make 1,000 units and if you want to make million units. Million units are obviously going to use way more plastic than 1,000 units. So there's going to be more cost to buy raw materials. Obviously, if you're making more stuff, you need more people. That's more cost because salaries. You need more machines, more electricity, more of everything to make more. So that's a variable cost. Fixed cost is the cost of the machine. You bought the machine and that's it. You spent $1 million to buy a machine that will make markers. And then the maintenance of that machine goes into the variable cost, right? Because the more you use the machine, more it breaks and you have to maintain it more. So that's common sense. So there is a fixed cost. You have to buy a truck. You have to hire workers. You have to, right? But then you have overtime, variable cost. You have maintenance for the truck, maintenance for machines. That's going to be variable cost because the more you use stuff, the more it breaks, the more maintenance goes in, right? So you have variable cost, you have fixed cost. Here's your fixed cost. Because it doesn't have an X in it, which means it's a fixed cost. These two terms are variable cost because it depends on how many units you make. Both of these terms depend on how many units you make, and that's going to be the part of variable cost. So now over here it says that we are going to make somewhere between 0 and 1,000 units of whatever you are making. So this is a very small production, obviously. Pretty much nothing is produced, right, for 1,000 units only. But let's make that is the case. So now we want to analyze this and take a look at what happens if we are producing 100 units. So 100 units produced. So let's do that analysis. Well, actually, before I do that, let's find the equations for average and marginal cost. I forgot to do that. So what's my average cost? It's going to be C of X divided by C. Oh, sorry, divided by X. So there's a square there. This is negative 0.02X plus 50 plus 100 over X. And that's the equation that I'm going to use to compute stuff. And then marginal is going to be C prime. That is negative 0.04 X plus 50. So I have my equations. So now I want to do the analysis of what happens if I make 100 units and what happens if I make 900 units, and understand what those numbers mean and what kind of business decisions am I making. Because if you make these, as a guess, your business must fold. I mean, there's no doubt about that. All right, let's take a look at the average cost. Average cost to make 100 units. Average cost to make 100 units. So what do I have? Well, just plug in 100. So I have negative 0.02 times 100 plus 50 plus 100 over 100. And that is going to give me negative 2 plus 50 plus 1 equal to 49. And I'm going to say that this is $49 per unit. That's your average cost. If you are producing something at on average at $49 per unit, you can't be selling that for less than 49 and somehow believe that your business is going to stay because you're at a loss. Even if you're selling it at 50, it's still, stuff comes up. You have to mark up much more than 49. But now with this calculation, you know that it costs you $49. So now you can start pricing your product to sell it. Because if it costs you $49 to make it, use common sense. Now, obviously, if you don't do this calculation, you don't know what the cost is, then yeah, good luck. Now, how about marginal? We'll see what this is used for, but let's now calculate C prime at 100. And that's going to be negative 0.04 times 100 plus 50. And that's going to be negative 4 plus 50 equals 46. And I'm going to say $46 a unit. No, $46 for 100th unit. And this is the first time where I get to tell you that the business model looks good because the average cost is 49 and your cost to make the 100th unit, so that one unit, right? You made 100 markers. The last marker that came out of that machine, the 100th marker, the cost to make that marker was 46. Then you say, wait, wasn't my price 49? Guys, average. The same thing like you drive from your home to New York. You start driving at 0. You stop at the stop sign, your speed is 0, right? But your average speed was 60. That means that you were going over 60 to compensate for those times that were going under 60 to average at 60. Well, if your average cost is 49, that means that the units at the beginning of the production were costing more to make than the units at the end of those 100 unit production. So the 100 unit costs 46. Now we go 900 units produced. Again, average cost to make 900 markers. I'll just say units. I don't care if you're making shoes or cupcakes or markers or cars. The calculation is the same. You just have different numbers, but it's the same. And you might as well talk about cupcakes. There's no difference. So negative 0.02 times 900 units produced plus 50 plus 100 over 900. This is equal to negative 18 plus 50 plus, this is going to be 0.11, right? I think so. Give me a second. I'm about to cheat on the calculator, right? So yeah, I mean 9 goes to 1 0 times, and then you make a 10. Yeah, it's pointless. I don't need the calculator. So what you get here is 32.11, right? Dollars. So 32.11. So you're gonna say 32.11 per unit. Ooh. If I want to make 100 units, it costs me 49 per unit. If I want to make 900 units, it costs me 32 per unit. Do we understand bulk buying and the deals now a little bit better? The cost of production and the cost of making things goes down the more you make, right? Because we went from 100 to 900, and look what happened with the average price. Let's take a look what is the cost to make the 900 unit. So how about marginal stuff? Marginal cost. You have your C prime of 900. That's going to be negative 0.04 times 900 plus 50. And that's going to be negative 36 plus 50. And that gives you what? Exactly. It costs you 14 bucks only in comparison to 46 to make 100 unit. This is $14 to make the 900 unit. So $14 for 900th unit produced. So if I am to sit there by the machine and grab the 900th marker coming out of that machine, that marker cost me 14 bucks to make, while the 100th one cost me 46. Now you want to know how much would it cost to make only one? Well, go ahead. Plug in number 1 in original problem. Right here. How much is the number 1? Number 1 squared is 1, so this is technically taking off 2 cents. So it costs you $149.88 to make one. To make one and shut down your production. Do you understand now why paintings are $10,000? There's only one made over 6 months period of work. So that piece of art that it's made by the artist, it took 3 months, it took 4 months, it took 6 months. When the price is $10,000, there is only one made, and the cost is large. You have the paint, you have all the classes you had to take to learn to paint and all the practice, right? You're never buying the painting only. You are buying all of the time that artist ever invested in developing that skill that you don't possess, right? Which is why you are buying that painting. And there are certain paintings, obviously the older they are, the artist is dead, you can't make another one, right? Can't make any new art and so on, so the prices skyrocket. That's the idea of having low units with a high cost. Art and painting, it's a perfect example. So as Tesla is increasing production, putting in new factories, new models out, and able to increase the production. You can see Elon Musk always talking about how many units they can produce in a week. Like most of his time is figuring this out, because he wants to make those predictions and he wants to fix the production, but he also wants to have a good costs so he can stay in business. Imagine if Tesla Model S was $30,000. The cost to make that is probably way less than 30K, right? But he can't put it at 30K because, first of all, he wouldn't be able to catch up with the demand. People will be waiting 30 years to get their cars. So, of course, put it at 80, 90,000 and get those people first who can afford that insane amount. So that's why he started with Model S and not with Model 3. Right? He started with the car, and then he went more expensive with the Model X at $140,000, and then went to Model 3, which is 40K, and then he's gonna make that truck, and that truck is better than everything he made so far combined, because it's pretty much indestructible. And someone said, "Oh yeah, he smashed that window." I said, "Do you have any idea what would happen to whatever car you have right now if you put that steel ball through the window?" That steel ball would go through your door and through you and through the other door and come out to the other side, right? And for him, made a little bit of a spider web on the window. I call that a win.
I think they said the window broke because they were hitting it with the sledgehammer, and that caused the window to fall down a little. And then they hit it with the ball and it broke the window. That's why they said.
Yeah, but even though to me was impressive, right? To me was impressive that the ball didn't go through and through the other. If I threw, and I have a really good car, if I throw the steel ball of that size through it's gonna go through both windows and then maybe to 3 sets of windows and 4 sets of windows. It's just right. But and that truck is going to be the cheapest of everything he ever made. And it's going to be order of magnitude better than anything that exists on a market by far. You're not just talking about self-inflating tires and bulletproof windows and bulletproof doors that are pretty much indestructible. I mean, if the train hits it, obviously. But, that's something that, in the cost, he has to work these equations out. And now you know how these things are done. And if you are thinking to have your own business and so on, and you don't understand this and you can't do this, well, you better hire someone who can. Otherwise, you are getting nowhere. Now, when I look at these costs here, I know that this business model is good, because as you can see, the cost is constantly going down the more I produce. And that is important. That is important, because I do not want to increase the cost with the production. I want to decrease the cost with the production. So I know that I have a good business model and that I can stay competitive and stay in the game. As soon as you start approximating these things and saying, yeah, it's going to be good, that's why more than 90% of businesses fail, right? Because it's very hard, it's insanely hard to stay competitive. And then you try to go against Musk and Bezos and these guys that are absolute monsters in computing these things. Their business models are absolutely brilliant. These people are brilliant. They know how to play the game. They know how to compute this. They are like almost different species of people than all of us, providing tens of thousands of jobs and all of those things. So there you go. So now, hopefully, you have seen a little bit of engineering, seen a little bit of economics, seen a little bit of biology, if you want to call it, or environmental stuff using population. You can use this also for garbage decay, and if you use the same formula in terms of mass, like m equals initial mass e to the negative kt, you can talk about decay of garbage, radioactive decay, and so on, so environmental sciences, and you can talk about the rate of change of amount of garbage in time, right? So how much it decays and how quickly we are recovering, reclaiming the land or whatever from those garbage piles and so on. So it can be, this lecture is not a lecture about one or two particular examples. This entire lecture tells you that rate of change is measured through the derivative, and if you have a formula, whether it's position function or garbage decay or population or economics, you are taking the derivative and you are measuring the change. You are seeing how much you are gaining or losing per unit of time in question. How much population you add in 1 year, how much garbage decayed in 1 year, what is your production per unit. So that was not per time, that was per unit. So the more I produced, the cost went down. Excellent. The derivative told me that my 900 unit is the cheapest one out there. Imagine if that cost came out to 60 and the average cost for the first 100 was 49. I know that my model cannot be sustained, because the more I produced, it costs me more. And I cannot price that product very well in that case. So all of these things are going to be out there for you guys to explore in your perspective areas, right? Respective areas. So look into how these calculations enhance your field of study, whether it's business, biology, or engineering, or whatever, and try to find the problems where this fits. We'll be back at 12:30, and we are going to finally go into that chain rule that I've been promising since early this morning. So yes, the 3.7, and I verified it. 3.7 is the infamous chain rule. So we'll be back at 12:30. If you have any questions, I'm staying on Zoom. Bye.